All right. Just the screen. Okay. Think
We can start out.
we can get started. Yeah. So, but thanks y'all for sticking around through the afternoon. I'm Chance Parrish. I'm a staff scientist at the National Lab of the Rockies. I lead a lot of our roll-to-roll membrane fabrication projects at NLR. And today I'm just going to be talking about some of the different challenges and opportunities in this space, ways that we can interface with NAWI 2.0 projects to help make pilots happen. So,
Chance, hold on.
yes.
You're like one of the principal guys in the lab, so you have enormous personal experience too with a lot of this equipment, don't you?
Yes.
Yeah, so
I can give a little
we
bit
don't
of.
have a huge crowd, so we might as well get informal and just kind of spell out. But Chance, you're likely to interact with a lot of researchers who would be coming through the system.
Yeah. So I guess maybe a little bit of background on myself too. So I did my undergrad at Virginia Commonwealth University in chemical engineering. Most of what I worked on there was on high temperature, high pressure phase equilibria for polymer solutions. So broadly, polymer solution thermodynamics and processing. From there, went to University of Minnesota, where I worked on fundamentals of coating and drying different processes and applications. And then went to Sandia National Labs, where I did a postdoc doing more modeling in coating and drying processes, especially for understanding how to scale up high throughput coating and drying processes. And then from there, went to National Lab of the Rockies, where since then I've been leading different activities, either in roll-to-roll membrane fabrication or in a couple different areas, fuel cells and electrolyzers. That was me. And roll-to-roll fabrication of some of the components there, both on the experimental side and then also on the process modeling side. So I think with that, one thing that we could also highlight are the many different projects in NAWI 1.0, this by no means being a comprehensive list, that have developed many different innovative cutting-edge approaches to try and solve water problems within the US and abroad. Despite all these innovations in some of these different water treatment processes.
So what big parts in the previous slide, Chance, can you go back to that slide? So these are all like NAWI 1.0 projects?
These are all NAWI 1.0 projects. So there's been a lot of innovation in these areas, not only for membrane-based technologies, but more broadly for different classes of water treatment technologies. Regardless of that, one thing that's been pointed out by some of the other big thought leaders within NAWI, like Jeff, Megan, is that despite all these innovations in materials and device scale advancements, there are still a lot of open questions about going to the larger device or pilot scale. So I think in this review that Jeff has pointed to before, one of the key things that they pointed out is when you scaled materials up to the module scale, there are many different phenomena that you can encounter that can limit the kind of improvements that you might see on the material scale in terms of how they would translate to improvements on the module and device scale. And this is one of the big things that motivates kind of NAWI's push for trying to go to larger pilot and larger device scales, is to try and take these technologies and accelerate them to the scale where you can actually probe the phenomenon that might matter. And this isn't really a problem that's unique to the membrane community. It's common to pretty much every other energy technology that's emerged over the last couple decades. So there's other leaders like those at Argonne, John and Lee, who've looked at manufacturing processes for things like lithium-ion batteries versus advancements at the material and the device scale for these systems. And just like for membrane technologies, these kinds of investigations tend to be dwarfed by all the smaller scale materials developments that ultimately need to be tested at the larger scale before they're commercialized. And that introduces or kind of connects to NAWI 2.0's broader research strategy, where we can leverage NAWI 1.0 activities and then try to get them, accelerate them to the pilot scale as quickly as possible, so that they can be tested in real devices under real conditions to understand where the limitations in actually implementing these technologies might arise. And to enable this kind of development or enable this kind of acceleration to the pilot scale, where you'll need large quantities of materials, large areas of materials, it's necessary to bridge this gap and inevitably, actually, as part of getting to the scale, try to navigate through the valley of death. To take a technology that's maybe been implemented at the small scale and the bench scale under bench scale fabrication conditions through where we see some of the work that we've done at NLR and NAWI 2.0 directed research, trying to scale up technologies like membranes or scale up kind of novel materials developed under NAWI 1.0 to larger scale membranes that can be tested in some of these early pilots before they go to larger scale pilot test beds. And inherently, as we're navigating through this process, there's a lot of risk in overcoming the valley of death and actually trying to make these kinds of materials in a roll-to-roll fashion to enable NAWI activities. One thing that we can see or that we tend to encounter when we're trying to navigate this process is that there are many barriers that we can get caught up on essentially that stem from a lack of complete information about what's needed at the pilot scale and about what we do at the small scale that can impact how a material might behave when it's actually made at large area and high throughput to enable these pilots. And this incomplete information, if you're not trying to, collect at the appropriate size scales, if you're trying to collect all this information at once when you go to finally commercialize a material, can ultimately lead to some very, very expensive learning opportunities when you do finally get to the commercial scale. So with all that background, I think today, most of what I'm going to be talking through is trying to address just various topics within roll-to-roll manufacturing scale-up and how they apply to NAWI 2.0 activities. So first, I'll go through an overview of roll-to-roll manufacturing with a high-level description of what these kinds of processes can look like, and then talk through what the major cost drivers are for roll-to-roll manufacturing, because this often informs the kind of directions for our research activities that we might take. From there, I'll talk about some of our scale-up research in NAWI 2, or NAWI, and how it applies to NAWI 2.0. So mainly, how is our research, how does it tend to be linked to different cost drivers? What these cost drivers are that we'll talk about in the previous section, and then kind of our approach in terms of how we look at different challenges that you can encounter that drive these costs. And lastly, we'll talk about how we can leverage these ideas to enable different NAWI 2.0 activities. So for a very, very simple description of roll-to-roll manufacturing, especially for, say, membranes, first you would have a substrate that is wound onto some roll that you pass through a system or a series of different rollers through a coating station, where at the coating station, a liquid precursor to whatever material you want to make is deposited onto the substrate. The substrate is then fed through a solidification station, where if the liquid precursor is a dissolved polymer solution, the polymer solution can be dried, removing the solvent to solidify it. Or if you say have a UV cured material, the material could be cured to achieve solidification. It's then passed out of that unit and then can either be wound up for subsequent use or can move on to other parts of the roll-to-roll process for different kinds of post-processing. Could be slitting, could be module winding. But regardless, this kind of technology or this kind of manufacturing process is used to make a very wide variety of different materials, different products. These can be ones that we're all a little bit more familiar with, like thin film composites that we might have for RO membranes. It could be highly complex multi-layer photographic films, or it could be things that we're not maybe as familiar with that are produced in a roll-to-roll fashion, like medical devices, transdermal patches for drug delivery. Now, from this simple description of a roll-to-roll process, there can be significantly more variation and complexity to these kinds of processes. I think Abhishek pointed out in his presentation. And for membrane specifically, these can cover many different kinds of configurations to make many different kinds of membranes. So you could have a system set up with coagulation baths so that you can make asymmetric membranes for either liquid or gas separation activities. You could have simultaneous multi-layer coating activities. Or here you could be making things like bipolar membranes for different bipolar membrane electrodialysis processes. Or you could be thinking of trying to make interfacially polymerized thin film composite membranes. Or maybe you feed a substrate through your coating process and then wet laminate in mesh support to make various different kinds of supported, whether they're ion exchange membranes or other kinds of separation membranes, before you feed it through a solidification process and get a membrane out on the other side. Now, of configuration you're using, there can be some very, very, very similar shared cost drivers that end up informing what kinds of research activities you might need to conduct to translate this kind of processing or translate a material through this kind of processing to get a low manufacturing cost. And additionally, to get materials of desired specifications for whatever application you're interested in implementing the material in. These, the ones at least we'll go through today, are your raw material costs, your processing speed, and your product yield. So over the next couple slides, for this portion of the talk, basically what I'm going to go through is at a very high level description of how to break down these processes into what the various cost drivers are for manufacturing a material per meter squared of the material. And we're going through those different cost drivers and see how many times they appear, and later portions of the talk discuss how how we structure our research activities based on the importance of these parameters. So here we have a very high level cost model for roll-to-roll manufacturing of the material. This is borrowed from the photographic film industry, where a lot of time and effort went into essentially developing these kinds of models because they were making a fairly low margin product at very high throughput. So it's very important to control all these different kinds of costs. But for us, if you look in the top right-hand corner of the slide, your unit product cost, your cost per meter squared, is going to be one of your final costs that factors into the price of the material. And this can be broken down into a production cost, how much it costs to actually make the material, your logistics cost, which can be how much it costs to keep it in stock if you make large enough lots, and also to distribute and transport the material. And lastly, overhead costs, which we don't necessarily go into too much, but could be things like maintenance repair, could be capital investment costs, and it could be things like, to be honest, R&D costs. The key parameter or the key costs that we'll cover today that influence how we approach a lot of our research activities are going to be raw material costs, which factor in your production costs, your fabrication costs, and then capital investment costs. And we'll look at how our key cost drivers, our fabrication, or how our key cost drivers of raw material cost, yield, and our production speed impact these three cost drivers that we keep in mind during our research. So first, for our fabrication costs, the fabrication cost, CC, which would be dollars per meter squared, depends on the production yield for that fabrication step. So how much of this product is in spec at the end of the roll-to-roll process. SMU, which is specific machine utilization, which I'll get into on the other slide, but it's essentially the amount of time it takes to make a unit area of whatever product we're interested in. And then lastly, you got your machine cost, CCM, which is the dollars per hour to operate the machine. Your machine cost ends up encompassing pretty much all of your variable and fixed costs to run your equipment. So these could be things like your energy cost, your labor cost, and then in some cases, the machine cost. Let's say you have a machine at Dell or at Kodak that runs or is available for a certain amount of time a year. If you're only making a small annual coating volume, maybe those machine costs get spread out over fewer projects. And if you're making a larger annual coating volume, they might get spread out over a larger amount of projects, and this machine cost will go down. But overall, it's important to note that our fabrication costs scale inversely with our production yield. So if the yield is low, your fabrication costs are going to be very high. Specific machine utilization, like I mentioned before, is essentially sort of material to make a unit of product. The specific machine utilization depends on a variety of different parameters, the most prominent of which tend to be the processing or web speed, and then your net product lot size. So your lot size might be for each production batch, how many meters squared you're going to be making per batch. And your process web speed is going to be how quickly you're operating the equipment to make the materials that you're interested in. Your SMU, your specific machine utilization, tends to be very, very sensitive to all of these parameters when you're operating at low process speeds. And this is one of the reasons why when we talk about roll-to-roll coating, we talk about high throughput. Because if you're operating at too low of a process speed, all of your costs tend to become very sensitive to any slight changes that you make in your machine utilization. And this drives, say, when you're making thin film composite membranes, a lot of the costs associated with making those membranes. It's also it can be very sensitive to your lot size. So here, I didn't show it on the legend, but this is essentially if you're taking a lot size from 10,000 meters squared of material up to 500,000 meters squared of material. So if you're making very small lots, your total costs for production of these materials can be very high. We can also see it does to some extent depend on the yield of your process. Raw material costs, this can encompass kind of the obvious, pretty much everything that goes into making the finished good. I won't go into a ton of detail on everything that factors in here, but two things that are important to point out is that your raw material costs depend on effectively two yields or however many yields would matter in terms of all the different ways you might process these raw materials into a finished product. So the raw material costs depend on the product yield from the fabrication process. So if your yield from your fabrication process is low and you're not getting a large quantity of in-spec material, your raw material costs are going to go up to make enough quantity of in-spec material that you might satisfy a given lot size. Additionally, this can depend on your upstream material yield from, say, a mixing process that might precede your coating process or your fabrication process. And overall, we're kind of keeping track. Your raw material costs are factored in once, your processing costs are factored in once, your processing speed is factored in once, and your product yield so far has factored in 4 times. And lastly, in terms of capital costs and equipment design, there are a lot of nuances that go into how a capital investment might be broken out into a unit meter squared of product. But in general, one of the important things to note is that essentially some of, for example, if you're trying to balance how you might be trying to lower your specific machine utilization to keep fabrication and production costs low, you may do that by raising your production speed. When you do that, your initial upfront capital investment costs tend to have to go up because you need larger equipment. And on top of that, when your capital kind of investment costs and the size of your equipment grow, your facility costs can also grow somewhat disproportionately and can sometimes undergo large step changes that many people may not expect to happen. So especially, let's say for a drying process, as your processing speed goes up and your dryer burden goes up, there are many things that you have to start factoring in, like regulatory considerations that wouldn't necessarily factor in lower processing speeds or lower processing volumes, the total size of the roll-to-roll equipment, and all the different upstream and downstream processes associated with them. And lastly, how these might affect things like HVAC requirements, and then even things like your power requirements for the facility. So in some cases, if you are operating large enough ovens or large enough curing systems, facilities may start needing their own substations. Additionally, you may actually not even be able to get, say, an electrically heated oven. You may only be able to use gas-fired ovens. So these are all things that can end up, as you scale up and go to larger scales, may end up factoring into final product costs. So in summary, if we're thinking about how costs can impact or drive some of the different research in this area, if we think about, kind of all the different parameters that showed up here, one of them that stands out is your product yield. So it's a very key factor that impacts your total costs. But in this kind of basic cost modeling, there's no definition about what your yield is. There's no definition about what controls it, which implicitly is going to depend on how you operate your process. And there's no information about how we define this. It's all product specific. So this is where, for our NAWI 2.0 research and where scale-up research, where we kind of like to sit and where we like to think about these problems. So one of the key goals, if not for NAWI 2.0, if we're trying to push NAWI 1.0 technologies and NAWI 1.0 materials up to the pilot scale, it becomes necessary to start trying to work together to actually define what yield is. So what we can think about is kind of a iterative pathway for us to come up with this definition. So we could scale up fabrication of materials developed under NAWI 1.0 using what we would think are some realistic fabrication or roll-to-roll manufacturing conditions. At the pilot scale and the device prototype scale, we can quantitatively assess the impact of these device properties or try and correlate these device properties on the pilot and device scale to pilot and device performance. And then pass that information back to try and define what yield is. So try and correlate impactful device properties to, under these conditions, whatever material synthesis and manufacturing conditions that were undertaken to actually make that device. And what we want to try and capture is information that we can use to try and define and control yield. Because that parameter shows up in so many different places in cost modeling, if you don't know how to do this, then there's no way to actually accurately capture and define what the cost of your material is going to be. And then if you're thinking about techno-economic analysis, to try and understand, say, for a given process like low salinity electrodialysis of brine, what your membrane costs need to be, there's just no way to actually try and benchmark against what you think you might be able to produce it for, unless you can do this. So essentially, what product specs will be required for success in a pilot, what range of material properties and manufacturing conditions can try and give these specifications, and then based on the answers to these questions, are there further innovations needed, and what further innovations might be needed? These are the kinds of questions that we try to answer when we're scaling up devices and when we're trying to make things on the roll-to-roll system. And that's kind of how we've, in terms of our directed research project, how we've tried to approach these questions and approach this problem. So we can, from some of the chemistries that we have in-house, we can try and identify or iterate some of these promising chemistries in our case for understanding how to scale up novel ion exchange membranes. And then we can take a few different pathways, both to try and actually fabricate these materials, and ultimately send these off for device and performance testing to then correlate that to the chain of making the new chemistry through fabricating the membrane. And we can also utilize computational tools like computational fluid dynamics and basically computational heat and mass transport simulations to understand how manufacturing conditions might impact our ability to size and design roll-to-roll manufacturing equipment. And then we can use TEA to assess the impacts of these different fabrication steps and chemistry on manufacturing costs. So as an example, for some prior work, Some of the things that we initially tend to start with are bench scale material refinement. So whenever we're thinking of working with a new material, there's almost always some initial challenges encountered when trying to scale it up to the roll-to-roll system that just aren't obvious based on common bench scale fabrication practices. So as an example, for membrane casting, it's very, very common to cast membranes from polymer solutions onto glass plates. That's the convention. Glass plates have a very different surface energy than most of the plastic substrates that people tend to coat onto for actual high throughput roll processing. And as a result, you tend not to get different kinds of fluid dynamic instabilities related to how that material will wet out the substrate. And in this case, if we're looking at this was casting a cation exchange membrane onto a PET substrate, what you can encounter is during the synthesis process, impurities that could be present that you would typically figure out how to design your purification process around when you go to scale up can start to cause challenges when you're initially trying to get these into a roll-to-roll system or get this kind of formulation in a roll-to-roll system for membrane manufacturing. You can get, due to the presence of some of these impurities, things like pinholes that reduce your ability to actually implement this kind of membrane in a real device. So it's something small that we can do at the bench scale to quickly and iteratively give feedback to people that are synthesizing materials so they can understand when they go to scale up. If they see a pinhole like this, it could be something that they can control and that they can iterate on in the synthesis and purification process to improve their ability to make membranes for subsequent device testing and screening. From there, once we've screened things at the bench scale, we then move them up to the roll-to-roll scale, where we have quite a few different capabilities that allow us to make various different kinds of membranes, whether they're dense ion exchange membranes or whether they're, say, asymmetric membranes on our existing equipment for either liquid or gas separation applications. One of the key things for the roll-to-roll equipment that we have that, reason why we tend to like working at the scale versus working on the bench scale is that oftentimes because of the kinds of features that we have in the system, we get a lot more control over our fabrication process than what we get at the bench scale. So we tend to be able to make things more uniformly, and we tend to be able to say a priori, before we go into the experiment, what conditions we need to control to get certain properties out of our materials. And just as some examples, we've got a heated slot die, where we can use both temperature and the inlet flow rate alongside the internal configuration of the slot die to make membranes of predefined width, of predefined thickness for a wide variety of different materials of very different rheologies. We can go down to very, very inviscid, very low viscosity electrodes. So these could be catalyst layers in different devices that people might use in water purification applications. And these could also be fairly thick membranes, as we'll show in a few slides. And overall, some of the main challenges that we try to address are this understanding of how our processing conditions can end up affecting some measures of yield that we can kind of guess or suppose upon before we actually know about all the different parameters that might control how a device performs. So an obvious one for most membrane materials tends to be thickness uniformity. And this is something that for a drying process, there are many different ways that unoptimized or just non-ideal configuration of a drying operation can cause different kinds of thickness variations, and in some cases, undesired phase formation to occur. So just as an example, whenever we're drying a coating, there's always going to be some shrinkage of the coating as it solidifies. As a result of that shrinkage, stresses can develop within the coating. This can happen whether you're working with a system that solidifies via solvent evaporation. It can happen with systems where you're UV curing as well, because there tends to be a lot of shrinkage related to the curing process. And this kind of shrinkage can lead to a variety, and this stress development can lead to a variety of different kinds of defects, ranging from curl and delamination to more kind of small scale millimeter or micron scale defects like surface texturing, kind of like orange peel. So you can form a texture that is actually like the outside of an orange, or you can get control of different phase formation, like what you might see for PVDF separators and batteries, where different crystal structures can form. And for us, on the drying side, one of the most common defects that we encounter when trying to make ion exchange membranes, just an example for some rollable cast membranes here, tends to be that orange peel texture. Because these materials are not only polymer solutions, whereas they dry, you can get stress development, they're also fairly hygroscopic. This kind of phenomenon can be sensitive to building humidity too. And on the top image, this is kind of a larger scale image of one of our membranes that's about 15 centimeters wide. And this is blown up what that kind of texture looks like, just to give you a sense visually of what you can see or what you would expect to see. And then if we look at changes in drying conditions, where say we switch to slower drying under hot air, this kind of stress development, it's slowed down. Enough time is given for this kind of, or for the polymer chains in this material to relax, and for stresses to dissipate. And as a result, you can get a smooth coating, which is a smooth coating on top of a transparent material. So comes off as just somewhat reflective. We can also, for many of these materials, think about coating process challenges, especially when we're looking at materials like some of the engineered thermoplastics, like PBIs and polyamides that are used for making gas separation membranes and for making hollow fiber membranes. So whenever we're thinking about concentrated polymer solutions and trying to bump up our polymer solution concentration, you can encounter a variety of different kinds of defect-forming flow dynamic instabilities that are related to the development of stress in the fluid while it's being extruded or coated. So essentially, what happens is you increase polymer elasticity is that you can get transitions to elastic turbulence, where stress building up and developing within the flowing extrudate or flowing coating can essentially dissipate in the form of turbulent flow. This tends to be extremely undesired in coating and extrusion processes because it ultimately leads to non-uniform coatings, or in an extruded material, it'll lead to stress development that when you start to try and handle the material, it'll cause the material to deform in ways that you wouldn't expect it to. So for an ion exchange membrane, it's going to deform when you're trying to plate it into the stack. You can also, for hollow fibers, get extrudate defects like this kind of sharp skin effect. And we can see this as we're playing with our casting solution concentration and temperature. And these effects can be somewhat non-monotonic because these elastic effects can also be dampened by higher viscosity as you start to go to higher solution concentrations. But what we see here in the top image at a 25 weight percent solution of BPS that we've dried to make ion exchange or a cation exchange membrane, you can get these pinhole defects that are much more severe than your blown up here, more severe than that orange peel defect that, while it's undesired for the orange peel defect, these pinhole defects comprise a complete failure of the membrane. Where if we go to higher solution concentrations and still maintain high casting temperature, we can get very smooth, fairly thick coatings. And we're trying to connect these kinds of activities that we've been conducting in our 703 to our NAWI device activities. We can think back to kind of what we were talking about earlier about trying to define yield for some of these different technologies as we go to pilots. So, just at a base scale, what have we achieved in terms of trying to scale up ion exchange membranes under 703? We can take custom ion exchange resin chemistries that we've either developed here at NLR or that may have been developed outside of NLR. We can scale these up to either small batches, 20 to 50 grams, that are enough to enable roll-to-roll coating trials, and that can enable us to do some iterative design on membrane fabrication. We can also take these chemistries and work with outside synthetic suppliers to make much larger batches so that we can do large studies for roll-to-roll membrane fabrication that would then enable other NAWI pilots to do their work. And then from there, we can take these materials and make a really wide variety of different kinds of devices and device configurations. So here we're just showing two examples for ion exchange membranes, where we can make thin individual layers. In this case, we're showing an 18 micron layer. But in other projects, we've gone down as low as 5 or 10 microns. And we can also make fairly thick cation exchange membranes and other ion exchange membranes. We're here, scale bar, 300 microns, we're at about 200 and 250 microns. So you can span quite a large length scale in terms of the kinds of devices we can make for people. And then from there, we can take those materials and conduct some in-house testing to understand how these might perform against commercial baselines like Nafion. And from there, build a chain to be able to take materials that we make on the roll-to-roll system, do some initial in-house testing, just so we can screen them before we send them out, take promising candidates, and then provide them to other NAWI activities, whether they be existing NAWI 1.0 projects or future NAWI device research projects under NAWI 2.0. And I'll conclude on the slide, but essentially just kind of circle back to the idea that if we're trying to connect back to NAWI technologies that have been developed under NAWI 1.0, as part of this process for accelerating these materials up to our pilots and our test beds, it's necessary to make these at large area, and ultimately to try and take the information that we gain at the NAWI pilots to define all the different requirements that we're going to need to actually design and assist technology developers in trying to commercialize these activities, whether under NAWI 2.0 or whether under emerging membrane center activities. So I think with that, we're taking up time, but I'm happy to take any questions, and I appreciate you all sticking around for the presentation.
Can you tell us a little bit more about where you're starting in this 604? Oh, sorry, 703. Where you started with 703 and kind of what, and these are specifically focused on the fabrication of ion exchange. Plus we got two of them. Yeah. So kind of tell us a little bit more about, maybe both of you, a little bit more about when you guys started, where are you now, and how are things going? As you said, your subtle hint of like yield. Yeah. Yield is really very dominant in this.
Yeah, I mean, so for us, for 703 activities, I think we started up last April. And essentially what we've been working on is scaling up or looking at a few different activities around cost reduction and ion exchange membranes. And also a pretty, I think, heavy component of it. We go back. Let's see. So essentially we had a key thrust dedicated to, I think, each of these pillars, so to speak. So identifying some or iterating on some promising ion exchange resin chemistries, production on roll-to-roll scale, and then associated either process modeling or TEA. We're trying to understand, build out the tools to enable scale up of these devices and these materials.
What was saying? Yeah. That's what I said.
Yeah, so essentially we got to, as Abhishek mentioned before that had happened, we essentially got up to this point. So we're able to take our materials, translate them to 702, complete some initial device testing, and now as we're waiting on year 2 so it'll get started up, next round will be starting to make a few different batches to send off to NAWI pilots.
So once you make the flagship membrane or how long does it take to make a logic one?
So in terms of, say, if we're making, so for this project, most of what we focused on, at least for 703, most of what we focused on is ion exchange membranes. So in terms of assembling it into a stack, most of that on the lab scale, we'd be testing these, in kind of these small stack setups. So
If you wanna make
a
that
day or
extra-
so, yeah.
Hey, how much
But-
square meters of material would you want to get to do a reasonable?
Right, so right now, our smaller pilot system is 9 inches by 10 inches. And then we can fit 10 pairs of memories. And 10 pairs, and then our larger commercial system is 18 inches by 14 inches. So that's. and then-
0.
Yeah, for 40 inches, so we can fit 600 pairs of memory, that's basically commercial system.
That's what we put the same.
Yeah.
Yeah.
Like the small pilots, yeah.
Yeah.
So,
Sorry. Well, I was just say the existing capabilities, this is kind of the scale of the existing capabilities that Abhishek mentioned in the previous presentation. So we can make on, say, this slot die. We can make up to about 8 inches wide. Whereas on other slot dies that we have and other equipment that we have, we can make up to the 30 centimeter wide. So we have a pretty wide range of materials that we can, or of sizes that we can make. We can get this as narrow as, say, 2 inches wide. So if you have small quantities of material that you want to test out, or smaller quantities of material you want to test out on the roll-to-roll scale, and you don't necessarily need to make something that's 8 inches wide to do that kind of testing, we can go through and make quite a few different iterations. And then I think to your question too about like module fabrication.
Okay, if I have like 10,000 time module. All of them.
And that falls more under the planned membrane center capabilities. So these right now fall more under the enabling kind of small pilot scale, that kind of, and then the device scale to help try and bridge that gap between what we're doing at the kind of small, coupon scale, and then what we're doing at what we would envision doing at the large scale on membrane.
Particularly for the hollow fiber, that's when we get the new equipment which can do 10,000 fibers. Range that will make that, but scale what we're looking is really you're putting it next to a distillation column. Using a switch element running through that fiber, that's like pure industrial scale. These are like all intermediate steps to go to that point. Yeah.
I also have a question about going back to the exchange membranes.
Yeah.
Exchange membranes can be used, for example, for desalination,
Yeah.
brackish water desalination. And then right now we are also working on brine membranes that has very low water content. So then we can treat the brine up to 200,000 milligram per liter. And the general unchanged membranes could burst, they cannot do it. And so I'm thinking here, are we going to develop a wide spectrum of unchanged membranes to tackle different needs, brackish water to brine treatment, and also to the bipolar electrodialysis?
Yeah, that's a good question. So year 1 and year 2 of the SOPO is geared towards kind of building out not quite capability development, but building out the workflow needed to try and answer these kinds of calls. And then year 3 and beyond is meant to engage more with the community to essentially provide this as an opportunity to engage and make materials that are needed for different kinds of applications. So this is to build out, and in some cases to build out some of the different kinds of solidification methods we might need to make like this wide range of materials. So just an example, this wasn't made using one of our conventional methods that I outlined before. So we've made these kinds of materials with different kinds of solidification methods that we're not quite ready to publicly disclose, but enable it, basically building out the workflow and building out the unit operations needed to try and enable this, being able to work with this range of thicknesses and with a wider range of materials has been the goal of the first year of the SOPO.
You have a question?
Yeah, so I guess just continuing on discussions and that, and I'll stick to bipolar membranes because of the what I explained. But just like looking at your materials, like visually they look very nice, like when they go off of the bullet hole. And so, and like I'm not familiar with how conventional fabrication of like unloaded BPMs is, but the ones that I've worked with in the past certainly don't look roll to roll. They look pressed, and there are like defects, and you can see kind of like grid lines where across like the material is processed. I'm not sure if that's, you know, I'm not sure if that's like the conventional way to make a BPM, if it is a roll to roll, or if these smaller batches that I get at the, you know, lab level are from hot pressing techniques.
So-
But I guess as just kind of like for me, and maybe for like the community, are there like, other than the material looks way better, which is usually like the eye test is really telling for a lot of like electrochemical materials. Are there like reasons to do like direct comparisons to conventional fabrication techniques without like thinking about these more functionalized or niche materials as you move forward to the membrane center? Like, are there like benchmark experiments that could be done now that show kind of why this is like so important immediately for people to be thinking about?
Yes. So, I mean, like, just an example, if you're thinking about bipolar membranes, conventionally, what my understanding is, both commercially and lab scale, they tend to be hot pressed or laminated. So, if we're thinking about that hot press or lamination process, you might spray a catalyst layer onto one of the sides of the membrane, and then take them, press them together under heat and pressure for some duration to try and affect enough chain entanglement that they don't separate as a result of being exposed to, say, a harsh environment and BPM-ED operation. That will inherently produce a different kind of structure than what you might make even sequentially casting on a roll system. Because when you're bringing the two surfaces together with lamination, it's a different driving force to try and drive entanglement and contact between the different layers. You're doing it, you know, say in a dried state and a solution state, they're inherently in different states. The different layers in different states when they're coming together and forming that interface. So as a result, you can get different performance. You can get, you know, and performance being electrochemical performance, but also mechanical integrity. So the way you take these materials and process them can have really uncertain impacts on what we define as yield. Because ultimately, things like mechanical integrity, things like your electrochemical performance are all things that go into that definition of yield that just aren't, you don't know them up front. And then if you're thinking about equipment design, you know, if we go back to, you know, this slide, quality control costs are baked into your production costs. That's another key component of the membrane center. If you don't know how you define yield, how do you define quality control costs? And you can't do any of this until you start making the materials at large enough quantities to test at large scale. So this is part of why when we think, okay, what are the things that we try and tackle when it comes to manufacturing research? So much of it is inherently built and intertwined into how we test the devices. And even before, aside from working on membranes and the work, say, that we've done in other spaces around DOE's DOE-funded projects, this has been the mentality that's guided a lot of the work in those areas. So, you know, I think even yesterday, at a very high level, without a lot of details, we were talking about how there are lots of membrane systems that just don't lay flat. And when you want to try and stack those into a device stack, that is a problem. That's a problem for automation. And things like that can be solved if you start looking outside at, say, different, you know, different products, you know, pulp and paper, you know, that kind of lay flat problem has been solved for quite a while. You steam treat it. It's like thinking like wrinkles in your
My shirts.
yeah, wrinkles in your clothing. That's exactly what I was gonna say. But it's, you know, but that kind of defect, you know, someone was saying they, in some cases, they just throw those membranes out.
Do what?
They just throw those out. They throw the curled up membranes out, and that's expensive, and you don't need to. And that, you know, if we think about, okay, another measure of cost, that's a finishing packaging cost or a device assembly cost that is absolutely unnecessary. As you go to larger and larger scales, try to make these devices a higher throughput, it's gonna stress test. It's gonna be a really big stress test. So a lot of these kinds of problems are gonna crop up. Yeah. Sorry, yeah.
We're on.
Oh, we're out of time.
Okay, we'll.
Yeah.
maybe Close it and have. Sure, thanks.
Yeah.
Or is this the same talk as yesterday?
No.
Excellent.
All right, yes, I gave a talk yesterday. I'll give another talk today, but there are some new things. So I'm Sarah Hesse. I'm an associate scientist at SLAC National Accelerator Laboratory, specifically SSRL, so the synchrotron there. And I'll give an overview of some of the work that we've been doing as part of NAWI, but then also just more broadly some tools that we have available. And so here's the team. Dean is actually sitting in the back. So he's one of the postdocs who hit the ground running, doing a lot of the characterization. And so just some acknowledgements. So this work is obviously collaborative. And so I'll be talking about what we're actually trying to do. So within industry, if you're looking at, and we've also heard from Abhishek, there's oftentimes a lack of like high resolution tools. And so to really understand these water treatment processes in real time. And so there's another barrier, I guess, which is also just visibility and communication. And so as a national lab, we can offer some of the tools, so spectroscopy, imaging, and scattering that can help reveal some of the failure mechanisms and transport phenomena and how is the material aging. So a lot of different things. So our goal really is to identify what the industry challenges are, and then to marry those basically to different advanced characterization tools. And so as part of our like translational strategy, we want to first identify the industry problems, so fouling, selectivity, loss, and then figure out which tools can help for that, and then really partner with industry and NAWI researchers to apply the capabilities. And hopefully that will accelerate materials innovation in these critical water technologies, de-risk the deployment of new membrane and treatment systems, and really create reproducible, scalable pipelines. And so we have a lot of different tools at our disposal. I'll talk about some of these in more detail in a couple of slides. But basically, we can look at structure and morphology using scattering, morphology and chemistry using imaging, and then chemistry using spectroscopy. And so this is from a paper that is currently in review. So we know membrane processes are complex. They're complex because they happen, a lot of things happen at different length scales and at different time scales. And all of that is happening together. And so you really need to understand these interconnected processes that are happening to be able to design materials that have the desired macroscopic behavior and performance. And so we had conducted over the last year kind of a survey trying to figure out what sorts of industrial challenges there are, and then figuring out what synchrotron tools are available to help solve those, but then also looking at the complementary lab tools, because we don't really want to be replicating what you can do with a conventional lab tool, but we want to be adding to it. And so we then also figured out, okay, what is the industry value here? So just one example, because this is an extensive list. So for example, cleaning effectiveness. oftentimes when materials are cleaned, you say, okay, the flux is recovered, and so the membrane was cleaned effectively. But that's not necessarily the case, because you could imagine that some species are being trapped within your polymer matrix. So you still have some other species in there after treatment, but it looks like the flux is recovered because possibly the polymer material changed as a result of that. And so there's various things. We found that ex situ techniques are really the standard, and there's a host of techniques, so SEM, XRD, EDX, optical methods that kept coming up. They're great, but they do lack this sort of in situ perspective of what's happening during operation. And so that's, I think, where we can help. And another thing that is quite difficult is figuring out what the organic deposits are on the membranes, because a lot of the membranes are polymeric. And so it's hard to really distinguish what's depositing after the fact from that like polymeric material underneath. Then oftentimes we talk to people and they conduct autopsies. And so those are really also just after the fact measurements. Another big issue is IP. So there, I guess, needs to be an avenue for dealing with that. So let me just
Sarah,
give.
can I ask a
Yeah.
question? In the course of kind of exploring kind of the industry relevance and the kind of like value, the value matrix, did you also look at, I thought that is Toray have a dedicated beam line in Japan, or like, do any other membrane manufacturers overseas have dedicated beam lines, and what they specifically do for those beam lines?
I don't know too much about overseas. I don't know if.
I thought
I know
Toray
they
has
have-
beam line in
Yeah,
it.
they have used beam lines significantly for boron rejection, for designing membranes for boron rejection, both beam line and fells. Very extensively, like for the
Yeah.
spectroscopy. I do not know whether they have in-house or they have a kind of access to.
I had the one of the Japanese water companies, and they said that the
Yeah.
Toray have a.
I think Springate has like an industry membrane
Springate,
type,
yeah.
steam line.
All right. So SSRL. So we have a lot of different tools. X-ray diffraction that really lets you look at crystalline structures. I'm not going to read all of these, but so crystalline structures. So for example, if you have titanium in your system, is it anatase or rutile, or what's happening to it over the course of time? X-ray scattering from the micro to the mesoscale, I would say. So polymer crystallinity, and then morphology and solution, for example. And I'll show some examples for these. X-ray spectroscopy, looking at local structures. X-ray imaging, so there's transmission X-ray microscopy that lets you look at meso and microstructures, and then X-ray fluorescence imaging, or XRF. We also have a cryo-EM facility that I'm not going to talk about, but that does fall under SSRL. So all of these tools have very specific requirements, and they do overlap. So Matt's actually in the audience. So we worked on reviewing a lot of the different tools and then matching them to different penetration depths, acquisition times, spatial resolution, and sample size. And as you can see that you can get quite a distribution of information from these different tools. So let's see. The way that a lot of these user facilities, or specifically SSRL, works is you have different ways of measuring your samples, ranging from standard, which can be more mail-in and rapid screening, to custom that require a lot of lead time to really plan those experiments. And so for membrane materials in particular, there are a few things that could be interesting. So For mail-in, it's X situ, relatively standard. We can run high throughput. So this is an example of our setup at the Saks Wax beamline where we can run, if it's in this configuration, about 500 samples.
Each one of those holes, sort of
Is a
port where
sample.
with-
Yes, yes.
Cool.
So what we've been designing there is these holders that we can ship to people and they ship us back their samples. And so we do that for films and powders. And then we also do the same thing for capillaries. And so it's designed, those are also designed in a way that the capillaries are secure in the little holder that we send. So there's these were examples of just like a film and water.
For example, if you have a spiral body, you cut it off, you can actually scan on a lot of areas. Like that, you get a full representation.
Yeah, and we do have a few different plates for this, so if you wanted to look at a larger material, that is possible. There is also that's the Saks. This is not an official mail-in program yet, so we're prototyping this, but it's working out pretty well right now. What that also allows us to do as a user facility is you can put in a lot more samples and run higher throughput and thereby then be able to concentrate on these like more custom experiments, just because this is very fast.
So is that usually done like overnight? You just start that before you leave? Or do users kind of do that on their own?
No, that was, so right now, that was me. And it's a learning process.
But I guess it's the ultimate goal to make it like an AI driven type thing.
Yeah, so actually a couple of weekends ago, I ran hundreds of samples. So, and in that case, also prepared some of the samples because there was issues with actually getting the capillary tubes. So I had some, so I was like, okay, I'll run them. But it's ideally we're moving towards more and more automation with this. Yes, so this is still in the testing stage, and we're getting feedback from people and also learning. So, you know, for example, being very clear that the sample needs to go in the center of that little hole there. So that it's been a learning experience, but it's fun. And then there's so an XRF program that I'm not too familiar with, but that's also in progress. And then this powder XRD program that's actually already rolled out, so that you can apply and get time. And you basically also just get a sample holder. It looks different than this one, but you get a sample holder and you can load your samples, send them in, and then you get data back. So the other thing that we have is, I'm going to call them standard or beamline specific setups. So these can be in situ measurements, but they're then usually in situ measurements that we have some sort of standard plan for. So for example, if you wanted to do some thermal annealing, mechanical testing, or some in situ probing of reactions. And this is where like each beamline is different. So what they call standard is going to differ. So those I would say have a low to medium barrier to entry. Just some examples of data that you can acquire. So from Saks and Wax, you can get structural information. So you can get information about the crystallinity and the phase composition, pore sizes, fabrication to performance pipeline, pretty low barrier to entry of its ex situ samples. And it is useful. So this is work that from my graduate school work where we were looking at these polymer solutions for blockopolymers. And we saw that depending on how you prepare the solution, you get very, very different membrane top surfaces. And so what this lets you do is you can take the data that you get with these Saks Wax techniques and inform the fabrication process later on. So that's just one example. There's also XRF. So what you see here is membrane cross section. So it's 1.25 millimeters across and then 0.25 millimeters down. And we looked at calcium, strontium, and barium and saw that they have different depth penetration throughout the membrane. You can also look at the top surfaces of these materials and just look at the distribution of your species on top of these membranes. And let's see. Oh, I don't know why it's not showing up. Okay, well, then there's also micro XRF. You can basically map the top surface and get information about the distribution of your catalyst, so in this case titania, over the top surface, and can thereby get information about how well your processing is working. There's also micro CT reconstruction. So there you can also look at what does this membrane material actually look like in 3D. How well distributed is my catalyst layer. And then as another thing, there are very custom setups. So those are the types of setups that really take advanced planning and then likely a couple of iterations. So that's where we can start looking at real-time characterization under realistic operating conditions. These are very specialized. They oftentimes require sample environment designs, and there's a relatively high barrier to entry. But it's high risk, high reward situation. And so what you can, for example, do is look at in situ flow cells for RO or electrodialysis or operando XAS. And so one example there is these experiments that were conducted at beamline 17.2. So that's one of our new beamlines. It's an undulator beamline that can run over quite an energy range from 6 to 20 keV. So you can look at a lot of different materials. We have a 6-circle diffractometer and multiple high-speed area detectors. Over the weekend, I ran at a few milliseconds in terms of acquiring data, so the speed of the data acquisition. And so it's also a large hutch and we can configure it to a lot of different things. What you see here is an example of this membrane that was put in, looking at the spacer, basically using X-ray imaging, which is a custom built instrument that goes into the beamline, and looking at the salt concentration across the membrane. And so this can all be done in situ, and there's a manuscript in preparation for that. But yeah, that's just one example of what we can do. And so are there other examples overall, other industries that utilize the synchrotron? And so as part of that review paper, we had looked at catalysis, at biological macromolecules, microelectronics, and then also energy storage and conversion. And these areas do tend to use the synchrotron quite often. And so the question is, can we also, within the water community, do that? Use these advanced tools? So with that, questions.
Well, that's probably too short. I don't know if you're part of this or not, but do you know the thickness of that transmission window?
I can find out,
That's
but
okay.
it's been a while.
Okay. That was one of the challenges we had building a similar system of the ALS, is making it as thin as possible, but still maintaining good flow conditions. So I'm curious if you all had the same issues or not, but I'll look forward to the paper.
But yes, that is one of the reasons why it takes a couple of iterations, that you have to tune those parameters to make sure that things are working the way you expect, but then also working for the X-ray side of things.
And do you anticipate being able to take these things to different synchrotrons? Like go over to the ALS close enough to you all, maybe?
We can.
Okay.
We for sure tend to design So for this, my goal with those setups was to make sure that we can at least within SSRL put them on different beam lines. Because that then lets you really look at the same setup on different beam lines using different techniques.
I think just getting to the operando stuff, but one of the challenges again we faced was we had a massive cart that we would wheel up to the beam line, and it's like we can't realistically mail this to an SLS2 to do stuff. So the whole operando stuff was more or less kind of track that ALS. So maybe something to consider, like how portable can you make stuff?
Yeah, that is for sure one of the challenges. I'd say for some of these it's okay. Where you for some of the institute also get an issue is like if you need different gases, if you need different temperature controls and all of that. So you really would need a self-contained system. It does get tricky, but some operando I think is possible.
I guess sorry to be hogging this, but is the goal for NAWI to kind of stay at SSRL and use different beam lines in SSRL, or?
Oh, that's not the goal.
All right,
The goal
I'm just curious.
Yeah, I'd say our goal is to, pardon the pun, but illuminate the potential of beam lines for the sorts of work that just hadn't, most of the membrane people weren't aware of some of these things. And so, Ethan and Greg and you are still, doing great stuff and in situ stuff, and so, and again, all these facilities have the added advantage that you have a user facility program. So that even apart from NAWI in particular, more membrane ideas come in on the user facility, track, the better, as far as we're concerned. So we're also trying to promote that out, like, hey, there's this pathway to do research.
And I mean, the other thing is we all have different expertise, right? We might be able to do things that other facilities can't. So I guess also just increasing that dialogue is important.
Exactly.
Yeah.
And I think like, the ALS soft x-rays a lot of the time, so the operando stuff
Right.
becomes nearly impossible. So
Right.
thinking about
So I think
x-rays and kind of working all around.
Good, thank you, Sarah. Okay, case dismissed.
As dismissed.
Session adjourned.
Congratulations.
Hey,
That's good, a long time. How was it?
it was intimate but focused.
Excellent. I can't wait to hear more. Good. I'm gonna go check on the other one.
Yeah.
I'm working on,
So we